Good morning, ladies and gentlemen. It's an absolute pleasure to have been invited here to do the John Saull Memorial Lecture. I had the pleasure of meeting John on many occasions in my time at the AAIB and also when I was sitting on the Royal Aeronautical Society Human Factors Group and Human Factors Group Engineering. And I always found his insights were very thought-provoking. He always had a viewpoint on some of our investigations and where we were going, and the sort of improvements that have come about. I myself, I am an engineer. I'm an engineer from background. I started off my career back in 1988 when I joined British Airways as an avionics apprentice. The reason why I got into aviation was actually through my father. He was an engineer as well. He worked in the engine overhaul shop at British Airways, and would come home at times and would talk about things that he was involved in. So a couple of notable things that he mentioned to me. One was after the 747 that flew through the volcano, and all four engines were then contaminated by volcanic ash. He was actually involved in the strip examination of those engines, and so was describing the conditions that he was facing as they were doing that strip examination. So he was mainly working on the RB211 and the JT9 large engines. But also, he showed me a photograph when I first joined the AAIB. He showed me a photograph that he had, and if anyone's ever been to Heathrow, it's not there now, but where the engine overhaul shop was in technical block D, which was on the engineering base, and you also had the short haul maintenance hangars were either side of that facility. So engine overhaul was at the front, and then there was component overhaul throughout the middle of this hangar facility, and then the hangars down the side. And this photograph was of a Trident, which didn't have its rear section. So the rear section had been top. And I was asking them, what was that? And they said, well, the aircraft concerned is ARPI, so Alpha Romeo Papa India. And for those that know their history, that was the Trident that crashed at Staines in 1972. But this accident was actually in 68, I think 68, something like that. This is where an Ambassador aircraft coming into land at Heathrow lost control on landing and then collided with parked aircraft at Terminal 1, one of which was ARPI and took the tail section. So that sort of got me interested in aviation. I was also really interested in electronics and computing at the time, so I became an avionics engineer. So that's really where I started, and spent my time working in the hangars until I then moved into technical services, and that's when I first really started getting involved in incident and accident investigations, and then moved my way through and became the fleet technical design engineer on 737. And around the time when the fallout from the accidents that occurred to the 737s in the States of United Airlines and the US Airlines aircraft crashes as a result of rudder hardover, so where the rudder had moved into sort of a position of because of the failure of the rudder PCU, because of contamination in the dual concentric slide of the power control unit. So one of my responsibilities of the aim was to implement the design changes to all the British Airways 737 aircraft as a result of that. And then in 2002 I applied to become an Inspector of Air Accidents at the AAIB and was successful. So I became an Inspector of Air Accidents Engineering, continued there until 2010, where I then became a Principal Inspector, and then in 2017 I then became Deputy Chief Inspector of Air Accidents, which is great. A few notable investigations that I've been involved in. So the Boeing 777 at Heathrow, I was the lead engineer and the investigator in charge. for that one, and I'll talk a little bit about that a bit later on. But I also supported the board of inquiry into the new mod XV230, which blew up over Afghanistan due to a fuel leak, which then ignited, which then caused what's called a boiling liquid explosive volume event, and that's what then did for the aircraft. But as most of you probably know, that led to significant changes into how the military go about their airworthiness oversight, setting up the MAA, setting up the Defence Accident Investigation Board. But certainly at that time, when I was involved as the advisor on the engineering side of things, quite surprising as to some of the airworthiness aspects around XV230 and some of the activities, in particular around the maintenance activities of the refueling gallery and the couplings thereof, where fuel seals effectively were fit and forget, even though the manufacturer had said they should be replaced. I can't remember the exact time period, I think it was either 5 or 10 years, something like that. But the issue is that if you disturb one coupling, because of the way those aircraft were designed and built, it was very difficult to maintain that system, because it wasn't within the tolerances that you would normally expect today. So they would disturb one coupling on the fuel gallery, and then would then cause a leak in another coupling, and then a leak in another coupling. So they were always chasing their tail around trying to support it. So I'm going to go back over the last 40 years. Now, why have I chosen 40 years? Well, my career started in 1988, but there was one accident that certainly I recall quite vividly as a 14-year-old boy at the time, and that was the Manchester fire. So it's a junior area. So the early hours of the morning in August, a bunch of holiday makers all going on the British Air Tours 737. And as the aircraft was on its takeoff roll, the combustor can failed due to thermal fatigue, and a section of that combustor can ejected from the JT8 engine and then penetrated the fuel tank, causing the fuel to leak and then ignite. So a significant fire. And then, of course, where the aircraft was then parked, it caused a lot of the fire to then be blown over the aircraft itself, which then penetrated into the cabin, and unfortunately several people perished as a result of that. The outcome of that investigation, if you go on an aircraft today, there's a lot of things we now take for granted that weren't there at that time. So things like evacuation alarms, the lighting on down the aisles, the materials that are used within the cabin are now such that if there was a fire, you won't get toxic fumes or that sort of toxic atmosphere as a result of that. And also, and some of the work that was done here actually in Cranfield with Helen Muir in particular, in relation to actually getting out of the aircraft and being able to evacuate. So the size of the actual doors and getting out, and whether you can pass through those areas. So there are quite a few of the sort of significant cabin safety things that have improved. And when you fast forward a few years, so the A340 there was in Canada, so that was an A340 that overran the runway on landing in Canada and caught fire, and everybody got off. So everyone was able to evacuate and leave that. And then more recently, the A350 that collided with the Dash 8. The Dash 8 was on the runway as the A350 came into approach. Again, significant post-crash fire, completely destroying the aircraft. But again, everybody got off that aircraft and everyone evacuated. So you can see there that the lessons that were learned from, what was a disaster in 1985, now would not be a disaster as such. Yes, you would still end up with a whole loss, but everybody. Now, of course, there were a few things that were recommended at the time on Juliet Lima that didn't find its way into what we see today. So one being water spray systems. So one of the recommendations that was raised was why don't we put in a water spray system similar to how in buildings, the idea being to knock the fire down to the extent that you can then get out of the aircraft. Of course, a lot of issues there is where do you get the water from, how much weight is involved, if it's inadvertently activated, how much damage would that actually cause, and what would be the tidy up as a result of doing that. So in the end, despite several trials, that didn't take place. Another one was passenger smokers. So you don't see passenger smokers. There are smokers for crew, but not for passengers. And the reason being, again, trials were carried out at the time. And basically the time it took you to get your smoke hood, put your smoke hood on, and then evacuate, you could have evacuated the aircraft. So basically, if you can remove the toxic atmosphere, then it's better to just get out of the aircraft than it is to be delayed in trying to put those smoke hoods on. Interestingly, the A340, one of the crew used the smoke hood, but then found that they couldn't communicate with the people to actually get them off the aircraft, so they then ended up removing the smoke hood so they could then actually coordinate the evacuation. So what seems like a good idea on the face of it really didn't get there. Now clearly most of that's about cabin safety, but of course here is around airworthiness. So a couple of the other aspects that really did come out from that one was the strengthening of fuel access panels, such that if there is an uncontained engine failure, it should not penetrate certainly those fuel access panels. So now you will see all that on those aircraft. And also it was found that the maintenance of that combustor can, so the combustor can had been subject to some modifications. And the recommendations from the manufacturer had not been appropriately reviewed at the time by technical services. So there wasn't really a process in place in looking at manufacturer's documentation and then putting in those changes into various manuals, procedures, or to actually do some action. So that led to changes. Certainly when I moved into tech services, there was a very robust system called the Technical Document Review System. Probably changed now, but at the time, every document that came in from the manufacturer would have to be reviewed and actions that were put in place. So you can see there are a few significant things. So what do we do at the AAIB? So our purpose is to improve aviation safety. We determine the circumstances and the causes of air accidents and serious incidents, and it's promoting action to prevent recurrence. But what's important is we do not portion blame or liability, and we are also independent of the regulators. So although we're part of the Department of Transport, we are functionally independent. The Chief Inspector reports directly to the Secretary of State of Transport for safety matters. So we have a lot of independence in relation to carrying out these investigations. Where we sit in the sort of triangle of investigations is at the top end. So we are looking at the accidents and serious incidents. But there are a lot of other investigations that are carried on, which is very important for the continued airworthiness of aircraft. So the mandatory occurrence reporting system, but also down into the company system, so the flight data monitoring processes that are carried on, the safety management systems that were mentioned earlier as well. They're all important in trying to identify some of these lessons and putting those in place and learning from them. But as I say, we're really the top of that triangle in trying to address that. Over the last 50 years of that we have on safety recommendations, so you can see there that we've gone through periods where we've raised significant numbers of safety recommendations, yet now we're around about 20 or so safety recommendations. There was a bit of a change of emphasis, around 2010, 2011 type period. We were raising safety recommendations on quite small things, and there was a feeling of, well, are they actually making a change? Are they effective? And actually, is there a better way of looking at this? So around that sort of time, we started saying, well, surely what we should be doing is encouraging safety actions, encouraging people to actually act on what we're doing, rather than beating them up with safety recommendations, or for organisations to wait until the investigation is complete, safety recommendation comes out, and then they do the action. So what we do now is we will obviously co-opt in the various different parties, and we will share the findings as we go along, and we will encourage them to do safety actions in order to address the safety issue, and then we will report on those as safety actions rather than as a safety recommendation. What that means is the safety recommendations we do raise are more significant, dealing with probably the more trickier areas, those that take a lot longer in order to work their way through. So that's why we sit at around about that sort of 20 safety recommendation mark. So what I'm going to do now is I'm going to talk about a few areas that we've investigated over the years in relation to airworthiness and maintenance, and where we've got to with these over that period. So I'm going to start off with a relatively minor one in some respects, which is tyre pressure indication systems. And the reason why I've started with this one is our first safety recommendation in relation to tyre pressure indication systems was in 1999. And that was with a 111, which on takeoff, I think it was, the tyre failed. And on the 111, because of basically the distance between the wing and the tyres, if you end up with a tyre failure, it tends to then penetrate through the flaps, the wing structure. So in this case, it caused quite significant damage to the flaps on the aircraft. And it was found that basically the tyres were not being, or the tyre pressures were not being maintained properly. So what happens with the tyre is, if you don't have enough tyre pressure in that tyre, you end up with fatigue within the sidewalls of the tyre, so in this area, to the extent then that will then fail, the air will work its way through, and they can just basically destroy the treads and the airflow, and then just basically destroy that area, and then you can end up with quite significant damage, as is shown in the image on the top right. Over the years since that recommendation, we've raised several other recommendations in order to try and get some means of having a tyre pressure indication system, so that you're able to work out. I mean, how many of you here have got a car that tells you whether your tyre pressure is proper? Prior to that, what were you doing with your tyre pressures? How many of you checked your tyre pressure daily to see whether they were? And exactly the same in a car. If your tyres are not at the right pressure, you could be steaming off down the motorway, and your tyre will fail. I mean, normally in that case, you could just pull over to the side of the road, but in other cases that could end up being quite tragic. So, on the basis of this, saying, well, if you can do it in cars, why can't you do it in aircraft? Now, in the early days, in the late 90s, yes, it was unreliable, and there weren't that many systems. But we had an incident with the 737 which had a tyre burst, causing again significant damage to the flaps. I actually did an investigation of several Embraer 145 tyre failures. There was a whole spate of them over a sort of 2 or 3 month period. Again, where it was finding that the maintenance organisation was not appropriately checking the tyre pressures, such that the tyre pressures were then reducing significantly. And then in Australia, again, they were finding another operator of the 737s was also having significant tyre failures. And again, they were finding that it was the maintenance of the tyre pressures that was not being done. So we fast forward now, and only in the last year or so, EASA have now introduced a change to the regulations such that there is now a requirement for a tyre pressure check system, either a tyre pressure indicating system or an appropriate maintenance system for the checking of tyre pressures. But that's taken 25 years from that initial recommendation to where we are now to get that in place. Health and usage monitoring systems. So the history of HUMS, which again is now something that is embedded in helicopter operations. But back in the 90s, there was an accident involving Chinook, the BWFC, in which the forward transmission failed. Because the forward transmission failed, the synchronization of the front and rear blades, they become synchronous, the blades then meshed, destroying themselves, and then the aircraft crashed with us and everyone on board. The actual failure was actually due to a modification that had been carried out in that transmission, but the modification itself had not been tested. The modification on the rear transmission had been tested and had been tested in a sort of environment. And there was an assumption made that, well, if it's okay for the rear, it's okay for the forward. So there was no check of that forward transmission. But it was also found that if you looked at the data, there was indications on the data that could have actually shown this degradation of the transmission before it actually failed. So as a result of that, we made a recommendation to basically have some kind of condition monitoring in order to identify potential failures. And then over the years, so that was in the 80s, so people go see in the 80s, and then we had a few S61 accidents, again, mostly transmission failures. And again, it was found that if you have some kind of condition monitoring process, you might be able to identify these before they become an issue. The CAA then mandated the installation of the health and usage monitoring system, and then subsequently mandated vibration health monitoring systems as well. So today, that's mandated, and indeed, whenever we're investigating a helicopter incident, we're looking at the HUMS and what was the HUMS showing to give us an indication as to whether that could have shown whether something was going to happen or not, whether actually it was there. There are still improvements that can be made, and it is constantly evolving. But what that shows is from those tragic events in the 80s, we've been able to introduce a system which therefore means we're not having as many of those now. So another couple of things within the maintenance area that is now very much embedded. So corrosion. So the image up in the top left there was the Aloha 737, which had a structural failure due to corrosion in flight. And one of the recommendations that was raised there by the NTSB was to the FAA to develop a comprehensive corrosion control program, CPCP. So as a result of that, various changes were made and been introduced. And for now, I think it's very commonplace for a CPCP program. Certainly when I was first starting in the hangars, this was evolving. It was forever evolving as to what the corrosion protection control plan is going to be. But of course, as now more and more of the systems evolved, it's now become sort of standard and commonplace to have those in place. The electrical system one, so the TWA 800, where an arc within the fuel tank itself was empty but had fumes. So an arc within that fuel tank caused an explosion, which then destroyed the midsection of the aircraft and then the in-flight breakout. Then you had Swiss Air 111, again due to a wiring failure within the cabin. And then also we did an investigation of 767, which had significant burning of the wire. And of course at the time it was all around the Kapton wiring, so the Kapton wiring issue, and the fact that the insulation can sort of carbonise and create this arcing. And of course, when you've got it in an area where you're near combustible materials, then you can end up with the fires of Swiss Air 111 because of insulation markings, particularly 800. So as a result of that, recommendations around electrical wiring to connection systems and inspections thereof of those systems in order to prevent that situation. We're also seeing now electrical failures in relation to older aircraft, in particular relay systems. So we're finding sort of relays that are been operating for several years, either welding or just having general wear and tear within the electrical system, and then causing issues with the electrical systems to reconfigure. So the latest one's really with the ATR and sort of electrical system issues there. So there are still some issues around the electrical systems, but the introduction of EWIS and the inspections thereof, and also the cleaning of electrical wiring systems, so you don't end up with loads and loads of dust and what have you. Again, has just reduced the risk of fires, or electrical fires in aircraft. And of course, the removal of Kapton and the use of different insulating materials for wiring as well. Sometimes changes are made which then has unintended consequences. So the Boeing 777 at Heathrow, so the aircraft was on approach to Heathrow, and at about 700 feet, the one engine rolled back to just above flight idle. 7 seconds later, the other engine also then rolled back to just under flight idle. Clearly not enough thrust in order for them to maintain height, and the aircraft landed short of the runway, fortunately within the airfield boundary, bounced, plunging the landing gears through the wing, and using the engines then effectively as the landing gear before then coming to rest in the hard stand. The investigation took us to 2 years in total. It took us 18 months before we actually were able to confirm what we suspected was the cause of the engine rollbacks. We're really confused as to why 2 engines that are independent of each other, which don't have the same control systems or anything like that, were rolling back at exactly the same time. So it was like, well, what's common and what's not? Now, fuel is potentially was one of those, but tested the fuel and the fuel was fine. So it wasn't contaminated, it didn't have excess water, so we weren't looking at any sort of issues there. So again, that was confusing us as to why that was the case. But we did suspect, was there a mechanism that could have caused some sort of fuel restriction? Now the data was showing there was a fuel restriction, so something had caused the fuel flow to be reduced. And we also had physical damage of the low pressure pump, which was showing that it was cavitating, which again was as a result of low fuel pressure when the fuel flow is going into the pump. So we did a load of tests, and effectively we were finding that when you run the fuel in a pipe that's then sitting in cold fuel, so the pipes run through the fuel tank. So the fuel tank is full of cold fuel, and you're running the fuel feeding into the engine through a fuel pipe. And you're running that at relatively low flows in mid-flight. And it was an exceptionally cold flight, so it was going through exceptionally cold air. But actually it was more the fuel itself, the temperature of the fuel, this pipe was running. And then through other tests, we found that there was these phenomena that at certain temperature ranges you could end up with what's called a sort of sticky ice. So this is where the water within the fuel can come out of suspension, out of the fuel, and then stick to the sides of the fuel pipe, and sort of almost like an arterial sclerosis of using ice. But even then, that wasn't to the extent that it would cause a fuel flow restriction. But what we have is then at the top of descent, when they increase the thrust, the fuel flow significantly increased, and the turbulence washed this ice that had accreted on the side inside the tank, which then created a snowball. And that snowball then found its way onto a device called the fuel oil heat exchanger. Now the fuel oil heat exchanger, it does two roles. One is it cools the oil, so it uses the cold fuel to reduce the oil temperature, but also increases the fuel temperature above freezing, so that when the fuel is then used for other control valves within the system, you're not going to have ice to then cause blockages of those really fine areas. So this snowball found its way into the face of this fuel oil heat exchanger. But the fuel oil heat exchanger should have been able to deal with that. It should be able to just melt the ice, and because basically the face of the fuel oil, the oil comes in just underneath that face. So the hottest oil is in that position. So we were thinking, well, surely that would just melt it. Now, a few years before, there had been a bit of an issue with the fuel oil heat exchangers on the Trent 800, such that foreign object debris was finding its way into these very fine balls which the fuel goes through. So it was causing these blockages, which was then causing some issues with the fuel flow. Not to the extent of causing restrictions, but just causing a few issues with the heat exchanger. So they came up with the idea of saying, okay, well, rather than having the tubes flush, let's move them up a couple of millimeters, so they were then protruding. So if you imagine that's the flat, so that these pipes are now protruding through. So the whole idea there was then the FOD would not find its way into the holes, it would just then sit on the flat plate. Great idea. But of course, when you get a clump of ice that then comes down, it was sitting on the top of these various pipes and was then being held off from the hot oil, so therefore not melting that ice and preventing the fuel from fuel getting through the fuel heat exchanger and therefore causing fuel starvation. So the unintended consequence there was a fix to try and prevent foreign object debris causing issues the fuel heat exchanger actually ended up causing another issue. Subsequently, the first thing that Rolls-Royce did once it got to that point was modify the fuel heat exchanger to remove those. What was good was we were able to run, we had a rig where we had actually proved this phenomenon. That was then used to test the modified fuel heat exchanger. It was then used subsequently to evaluate all fuel oil heat exchangers across all engine types. So it was used, the FAA basically used that to validate that process. So today, I mean, I think there is now a requirement of that test to be carried out to prevent that. The thing about sticky ice and ice formation within fuel pipes, though, was known about in the 50s. So we did a literary review right at the time, and we found that Lockheed, with their electrodes, were having a lot of issues of ice build-up, and they'd actually done a lot of research around where was this ice coming from, how were they getting it, and they'd all done quite a lot of things around this phenomenon of certain temperature ranges of ice. We were just able to add to that knowledge base. And then the B-52, again, that sometimes would have issues with ice build-up and causing issues with fuel flow. So, in some cases, the answers were there. It was just trying to find them. The other one that's on there is an AS332 L2 helicopter. So this was in 2009. So the helicopter was operating out to one of the rigs in the North Sea and suffered a catastrophic gearbox failure. And the rotor had separated from the helicopter. And that was because one of the second stage planet gears had failed, therefore causing that disintegration. Now, the day before, an engineer had taken the chip detector out from the gearbox, and there was a chip on that chip detector. The manufacturer basically said, it's fine, go flying, it's not an issue because it didn't have enough that was within this sort of box area that they have. But what Airbus helicopters had done was to reduce false removals of gearboxes. They had put a ring of magnets in the gearbox. And this ring of magnets was there to collect chips. But that was before the chip detector. And of course, what it was is the idea was to avoid chips from finding its way from one part of the gearbox to another part of the gearbox. But in doing so, they effectively disabled what was probably one of the primary detection means for a degrading gearbox. So we don't know whether, if that ring of magnets had not been there, and that engineer, when they removed that chip detector, would there have been more material on that chip detector, and therefore the gearbox would have been replaced. There was another gearbox available. So, it could have been a disaster that could have been averted. Now, we do actually know because, unfortunately, there was another accident involving a similar type LMOJF. Again, a second stage panic gear failure in exactly the same circumstances, so the failure mode was the same. But that had already had the ring of magnets removed. So it is unknown as to whether that would have taken place or not. But the point here was something that was introduced to deal with one issue created another. So it's those unintended consequences. So one thing that we're struggling with now, so this is more something we've had from a couple of investigations. So this is around critical parts. generally in helicopters, and we've done a few investigations now where we've noted that there's been a failure. So the SKP, it was a failure of the bearing within the tail rotor drive shaft, which then it welded the nut, which then wound the nut off the end of the tail rotor. The tail rotor then drove to its full extent, and the loss of the helicopter, because it just basically then was constantly having to rotate. That bearing was not, although it's in the transmission part, it was not something that was regularly and routinely looked at. So the bearing, if the bearing was removed, and because of during an inspection or what have you, it then wasn't being investigated as to why that has failed, what's the failure mechanism, and are there things that can be learned from that, which could then either be a change in the design. So in this case, you know, are ceramic bearings really the appropriate bearing for use in that helicopter for that load spectrum? And we do have some questions around the testing that was carried out at the time by the NRO as to whether they did the appropriate testing for that particular bearing in the tail rotor. But it was more around, you know, learning from that. And in the same case, we were, you know, quite surprised with Airbus helicopters. Not only in this, but also with other investigations, where, you know, bearings, or in this case gears, would be rejected during overhaul, but they then weren't being looked at as to, okay, why have they been rejected, and what can we learn from that, and then feed that back into the original design assumptions that were done at the time. So we had a couple of ditchings of helicopters in the North Sea, which was due to a failure of the bevel gearbox, and the original fatigue calculations that were done at the time had never been reviewed. So basically, they were done at the time, but they got into service and never reviewed that. Now, the failures in that case was due to stress corrosion cracking, but even so, we were saying, well, how are you learning from experience in operations? So we got a few recommendations around critical parts and the identification of critical parts and how they should be maintained. There's a bit of a difference of opinion at the moment between the EASA and the CAA and how that's being looked at. EASA are tending to rely more on the manufacturer and not really looking towards the CAA and taking a different stance and taking it seriously. But certainly, you know, sort of identification of critical parts and going through that process of you know, learning and looking at these parts and examining and then coming back and feeding that back into those design assumptions, maintenance assumptions, and making those adjustments. You know, I think we should do that rather than waiting for a disaster before then having to go into. So next topic just to talk about is on maintenance side of things, so various investigations in relation to maintenance. I'm sure you're all familiar with the 111 window. I think it's fairly infamous in a way because really it was probably the first in-depth maintenance human factors investigation that was carried out. For those who don't know, the aircraft in flight and the window then blew out. So the windows on the 111, they're not plug-type windows. So they're windows that they come in from the outside and then bolted around the outside. And the aircraft had been in maintenance, I think the day before or days before. And the window had been replaced. And in this case, yeah, the window blew out. The captain was then held by one of the cabin crews. The cabin crew managed to grab hold of the captain, otherwise he would have been ejected. Even so, he was still hanging out the window, and suffered quite serious injuries as a result of that. But really the investigation was around why did the window fail. And in this case it was found that the wrong bolts had been used on the window for securing it. At the time it was being replaced, the engineer concerned basically used a shadow board which had a whole load of general spares on there, and was going and just comparing, you know, the bolt to the ones on there, and then selected one that just wasn't quite the same, so therefore didn't have the same grip strength, and therefore didn't return the part of the window in place. Quite significant changes. I was working for British Airways at the time, and yeah, like everybody else, I had a black book. I had a toolbox full of useful things that could be used. You know, the black book of, okay, well, if you can't find this Airbus part number, this Boeing one or this Lockheed one might work. I mean, it's surprising how many times you went onto a Boeing and you went to go and undo something and you find it's a tri-wing. And you go, tri-wings are only used on Lockheeds, they're not used on Boeings. So obviously there was a practice that was going on quite regularly. And similarly, you went to stores and you wanted to go there. Yeah, there were trays and trays of nuts, bolts, wires, connections, what have you. And you would select the one that was closest to the one you got. But of course, in this case, it was a disaster. So obviously significant changes were then introduced. Those boards disappeared. Quite stringent process for management of spares. I think people still use black books, but you know, really they were, you know, really frowned upon. Our avionics cupboard disappeared, which was full of stuff. But I think, you know, now, you know, that would be anathema to anyone in maintenance. That sort of practice. So yeah, that investigation there, you know, really did lead to those significant changes. But other things in maintenance are still happening. So there's a couple of images here. So this is a landing gear on an Airbus A320, and it's sort of associated with this other A320 here, because it's around the use of manuals and at the time. So this one was the aircraft had come into land and had a heavy landing, so it suffered a heavy landing at the time. And the engineer concerned, it was the first time he was using the electronic manual system. So prior to that, the engineer had used basically the paper-based or the microfilm type system. So he never used the electronic system from Airbus. So had a look at what was required and selected the wrong inspection for a heavy landing. And that heavy landing check didn't require the aircraft to be jacked. It just required, have a look, see if you can find any creasing in the structure, and you know, just have a general look around, and if it's all fine, then you can go flying. Whereas if you'd actually followed the manual properly for what was required, then the requirement would have been to jack the aircraft. If they jacked the aircraft, you would have actually found that there was significant damage that had been done to the landing gear, to the extent that the only thing that was holding the inner cylinder to the outer cylinder were the hydraulic hoses. So that aircraft actually went back into service, passengers on board, took off. As soon as it took off, they got all of the various air ground warnings, so a lot of system failures as a result of that. So they came back into land, and as a result of that, they did the jacking, and that's when they found that damage. What's interesting though, and this is a bit of a testimony to the strength of this landing gear, was that actually if you did a pressure extension check, it was fine. So a pressure extension check, so it looked okay, on the ground it looked okay. It It was only if you jacked it or if it was, yeah, so that was misinterpretation of the manual. This one was, the aircraft had been into maintenance, and as part of that maintenance was a biocide treatment. So the fuel was treated with biocide to prevent build-up of bacteria within the fuel tank. But again, the manual, and it was an electronic manual, was misread and misinterpreted to the extent that the amount of biocide that was actually added to the fuel tank was orders of magnitude more than what was required, which in effect contaminated the fuel, so that when the aircraft then subsequently flew, it suffered an engine failure as a result of that because of the contamination of the fuel. So again, it just shows there around the interpretation of those manuals. And in both cases, it was down to being an electronic manual system and trying to follow that electronic manual, and to the individuals concerned not effectively having that ability to follow it, either because the instructions weren't clear, or, as in the case of this one here, not being trained or knowing how to use those electronic manuals. Cowling losses. So we're still seeing cowling losses. So this is all around the cowlings not being properly latched following maintenance. So that was EUE, British Airways A320. But there are several other examples that we've seen over the years. What there is now is that there is a requirement. So what's been added now to CS25 is that there must be a reliable means for verifying that the cowl is secured prior to takeoff. It's taken a while to get to that position. I think there is still a preference that we would think the crew to be aware the cowling is open. At the moment, what it's mostly using is flags or some kinds of means that, you know, if you look at it, you can see that the cowling is not secure, and relying on the crew doing their walk rounds to be able to identify that the cowling is not being closed. But yeah, personally, I think there could be more, and that is to have some kind of system to alert the crew the cowling is not secure. You know, as we've seen, you know, that can be significant. In this case, it caused a fire, and you know, that could have been quite significant at the time. And one in the top right, that was a 777 shortly after maintenance. So during the maintenance input, the engineers had accessed the centre fuel tank, and they hadn't recorded it properly. So at the end of the check, there was an assumption that the fuel tank access panels had been installed, but in this case, it hadn't. So actually one of the centre fuel tank access panels was still open. The bag of bolts securing that access panel had been tied. It was sitting, the panel and the bolts was on the aircraft and had been tied up at that time. So there was no visual indication that panel was not installed in the aircraft. So fairly typical human factors there, where the aircraft was released, and it was only once the aircraft then took off that basically you ended up with a significant fuel leak coming out of that centre fuel tank, as you see there. Again, I think fortune in this case that it didn't ignite, and we didn't get a significant fire. You know, as we know, like Concorde at the Gomez, that did ignite, and the aircraft was lost as a result of that. But it still shows that there are still human factors within maintenance, and it's being able to learn from those, and that's where it's important with the safety management systems, being able to learn, you know, from these events and from these near misses, so to speak, in order to do those improvements. Generally, when we get involved and we're doing an investigation, it's gone beyond that sort of point, and fortunately, we would hope that actually it's being dealt with at that next level down. So that was a sort of run through of various different things that there's a lot of other areas I could have spoken about. I can talk for days on all sorts of different investigation activities. But as we know, things are still happening. I'm sure you're all following what's happening with the MD-11, with the engine separation. Certainly I'll be interested in what has caused that engine separation. I'm sure a lot of people are doing similarities to the DC-10, which obviously was a maintenance-related issue at the time, where the engine was being fitted using a lift, so improperly being fitted. I think people are speculating. We shouldn't really be speculating at all on the MD-11. But obviously, we still got the events. I just read a report recently. The NTSB have issued an American Airlines 737, which had modifications done of its braking system, the anti-skid system, and when they installed it, they'd cross-wired the sensors such that the anti-skid system would not be operating properly, so the locked wheel would not be released, and cause a one-way excursion. So we're still seeing that these various issues are taking place and are happening. So there are still lessons to learn and improvements we can make. However, where we are overall, so this is statistically the number of fatal accidents is significantly reduced from those days in the 80s. And a lot of that is through the lessons that have been learned from accident investigation, but also lessons that have been learned from other activities as well. But we can do better, and that's really the role of you guys as well in what you do, in looking at those awareness aspects. With the aim of getting to the point of no fatal accidents. That's about commercial. Obviously, we also investigate general aviation, and we're still seeing the biggest killer within general aviation at the moment is loss of control in the air. Most of that is due to how the pilot has handled situations, so engine failure, and then not handled the engine failure very well when putting the aircraft down into a field. Or in some cases, just having some kind of event, which is then causing them to lose control, either during an aerobatic maneuver or doing an inappropriate control or something. But we are also seeing, the usual issues of maintenance, aging aircraft, and the various challenges around those. So, there are still things that still improvements within the general aviation area as well. So it's not just commercial, it's also general aviation. And for us moving to the future, we are the Space Flight Accident Investigation body. So we've done a couple of investigations already. So the Virgin accident, and to a smaller degree, one of the Tesla, SpaceX explosions where it caused debris to be rained down on one of the overseas territories. But we're looking forward to the first launch, the first vertical launch at Saxaboard. But what we don't know is what are they going to throw up? What are the sort of challenges and areas and lessons that we might need to be learning from that? So that's a whole new area for us around space flight. And as John was saying earlier, the other areas of electrification, urban air mobility. For us, remote pilot aircraft systems, especially those operating beyond visual line of sight. And the scrutiny of some of these unmanned aircraft, certainly at the lower area, sort of the model aircraft area, and the oversight of those, which I know is a challenge for our colleagues at the CAA in trying to put the appropriate controls on that to make those safe as well. So I've done a lot of talking. I'm starting to lose my voice. I hope you found that useful, and yeah, any questions?